Welcome to the Friday Transportation Seminar here at Portland State University. We're very pleased to have Dr. Grembek, who's the co-director of the UC Berkeley Safe Transportation Research and Education Center, so SafeTREC. And we were just joking, it's the other trek on the West Coast, down where's the trek here at TSU and the trek down at UC Berkeley. So Dr. Grembek is going to talk to us today about the safe system approach. So turn it over to Thank you.
Great, thank you. Hi everyone. So I always tell people when they come to present that they should have their presentation, then can have a plan B in case they have less time, and then plan C, they only have 5 minutes. But I'm really good at saying it, I'm not that good at doing it. So I'm supposed to go to my plan B now, but I don't have one. So kind of bear with me if I go a little bit faster. I'll try to make sure we're done on time. Now I'm trying to figure out, supposed to look at that the camera or that camera or some combination. So this one?
Yes, and your attendees here, feel free to look at them too.
Okay. Yeah, no, I was just trying because there's a camera in the back. I wasn't sure which one is that. Thank you, Chris, and the track team for inviting me to speak. I really appreciate this opportunity to present to you some of the research that we're doing, and then also more specifically, I appreciate the opportunity to charge my cell phone. As some of you may know, California this week has had a lot of electric outages, and it was actually part of and it was part of PG&E's public safety power shutoff. And they identified 3 elements as to why this shutoff was necessary. 1, low humidity, sustained winds, and then dry fuel on the ground. And as a result of that, they said that they need to make a significant major shutoff to maintain safety. And when I heard it, I needed to start thinking of how does this relate to transportation safety. And I noticed that they are very focused on what are the things that can make it unsafe. And then their response was, sorry again. And the response was, so to maintain safety or to produce safety, we need to cut off the power to more than 730,000 accounts. These are not people, people is way over 2 million across 34 counties for 3 days. So the UC Berkeley campus was shut down for 3 days as a result of this. And the outcome, as was described by PG&E, is good because there was no fire and no one got hurt. But and that would be true if their goal is to produce safety. But if you're able to produce safety by shutting off the power, you're not quite fulfilling the mission of your organization. Because the way I see it, their purpose is to provide electricity subject to a set of constraints. And that's really related to what I'm going to talk about today, which is the safe system approach. And the idea is that we need to provide mobility, but again, subject to a set of constraints. So what I'm going to talk about today is 3 things. I'm going to start by talking about the safe system approach and how it relates to safe vehicles, safe roads, and safe speeds. Safety buffers, which are all of these multi-layered components that together provide the opportunity to build a system on which no one can be severely or fatally injured on. And then at the end, touch about some of the policy implications, because we do want to be able to translate this to practice and to policy. So as I said, and I really appreciate PG&E's timing, the purpose of the transportation system is to provide mobility. Now, this isn't necessarily a consensus definition, it's more my definition, but if you pause for a second and think about it, I'm sure that you'll agree that at the end of the day, this is the overarching goal. But it's always subject to a set of constraints. We need to provide efficient mobility, cost-effective mobility, equitable mobility, sustainable mobility, and the theme of my talk today, safe mobility. Now, all of these constraints are equally important. I'm a little bit biased because I do traffic safety research, but in my mind, the safe mobility is the most important one because it's a transportation failure that results in someone not getting home. So is our transportation system safe? Well, let's look at the numbers. Or this orange curve represents the fatality rate per 100 million vehicle miles traveled. As we can see, for decades, it's been dropping. So there's some demonstrated improvement. Maybe we are on the right track to achieve safety. The number of fatalities per year, the numbers are very high. In California itself, just in California in 2017, there were over 3,600 fatalities. In the US, over 37,000, and globally, more than 1.3 million. So it's definitely not a safe system, and we're definitely experiencing a lot of fatalities. Well, but maybe it's just a numbers problem. Maybe there are just so many people traveling. So of course, there are going to be a lot of fatalities. So let's look at how it compares to other causes of unintentional death. And what we have here is data from the CDC about the 10 leading causes of injury deaths by age group. This is data from 2017. And when we look at unintentional motor vehicle traffic, it's either the first or the second cause of unintentional death across the US. So not only are we seeing very high numbers of fatalities, we're also seeing that relative to other unintentional deaths, this is a leading cause of death. So what is this safe system, or this aspirational safe system that we're talking about? What we have here is, it's not a PG&E employee, but we have here a construction worker, and he is working at heights. But we can see he has a cable, a safety cable he's holding onto. He also has a safety harness that is another layer of protection in case he lets go or has to let go. And what is not shown in this picture is a safety net underneath. So what they have in some parts of the construction industry is they have this layered, redundant approach to provide safety buffers because they understand that at some point things might not go according to plan. So using this way of thinking, with this concept, we're defining a safe system as a system in which people cannot die despite human error. It recognizes that we're going to make a mistake and we don't want that to cost our life or someone else's. So is our transportation system dangerous? Let's look again at how can we define it? And here it's defined as a system in which people can die with no human error. It can be a minefield, avalanche area. So also if you did nothing wrong, you can still die. So we're calling that a dangerous system. So we're not a safe system, but we're also not a dangerous system. So what is this transportation system that we have? So it falls in the middle. It's an unsafe system. And an unsafe system is one in which people can die through human error. So if all of the system does exactly what it was designed to do, if all of the road users behave exactly as they are expected to behave, maybe it will be a safe system, but the reality is, as we know it, is that things do go wrong, and then as a result of human error, people still die. Now, and this, all of these deaths, we know that at the end of the day, it's not necessarily the crashes that are a problem, but it's more the kinetic energy. And it's the kinetic energy that is the transfer of this problem from a crash occurring to a fatality or severe injury, because it's this kinetic energy that our bodies cannot quite sustain. So why is kinetic energy so important? So as I said, first of all, it's because that is the source of injury. But second, it's also because our traffic system is multimodal. And we have a variety of road users. We have pedestrians, we have bicyclists, we have powered two-wheelers, cars, SUVs, buses, and trucks. And actually many more modes. And these different modes, they carry different amounts of kinetic energy based on their mass and their velocity. These are just numbers for urban environments. They're not necessarily accurate of my weight also, but they help us demonstrate that there's a very big range between the 0.1 kilojoules that are carried by a pedestrian and 57, 500 or 600 times more kinetic energy that's carried by a car. Now, if this is at urban speed of 20 miles per hour, you put that on a highway and the kinetic energy is even much greater. So we see that we have this multimodal system, and as a result of that, we also need to think of safety in the multimodal context, because there are all these different modes that are mixed together, carrying very different levels of kinetic energy, and that imposes a lot of complexity to our system. So we try to think about that in a little bit more structured manner. And in our center, we developed this multimodal injury matrix. And what we have here, we have the same modes that I described before: pedestrians, bicyclists, powered two-wheelers, cars, transit, SUVs, trucks, and then an inanimate object as one of the modes. And the rows represent injuries suffered by these modes. The columns represent injuries inflicted by a mode. Now, suffered and inflicted does not necessarily mean fault, but it means there was a result. There was a crash between two modes, and as a result of that, this mode suffered an injury. By definition, the other mode inflicted that injury. If they both suffered an injury, then it counts twice, because there were two injuries that were experienced. So what it means is that element Xij of this matrix represents the number of injuries that were suffered by mode I, X1, and inflicted by mode J, X4. Okay, so if a pedestrian crashed with a car and only the pedestrian suffered an injury, X14 would have 1. If both the pedestrian and an occupant of the vehicle suffered an injury, then X14 would get the value of 2. Okay? And then we populated that data for injury crashes in California. And it's kind of a nice snapshot of what modes are inflicted in suffering injuries from other modes. And I'm not going to go into the details of what the different cells mean, but I'll talk much more about the aggregate. So when you add up all of the rows, you actually get the numbers that we're usually talking about in traffic safety, and that's the sum of pedestrian injuries, the sum of bicycle injuries, and so on. But these sums, what they give us an opportunity to do is to see what is the relative vulnerability of these modes for the California mode mix and built environment. So if we take, so if we take the 40,202 pedestrian injuries in California, or injuries suffered by pedestrians, and we divide it by the number of injuries inflicted by pedestrians, we get a proportion, or we get a rate, and we're calling that rate the relative vulnerability. So in this case, it comes out that pedestrians are almost 37 times more, or they suffer 37 times more injuries than they inflict. Now, usually at this point, I get a question: how can a pedestrian inflict an injury on the car? And the answer is, well, first of all, it doesn't happen much, but it can happen that the result of a crash with a car, there will be a rollover, a vehicle might crash into some roadside elements, and as a result of that, the car occupant can also suffer an injury. Now, when we do the same across these different modes, we'll get this vector that is organized in a way that's the same as the kinetic energy that they're carrying that we saw before. And it helps us illustrate about how complicated it is to design for a system with so much variety of road users and kinetic energy. So that all of these realities, that there's so many crashes and there's this multimodal misalignments, lead us to thinking about what can we do to change to move the needle from our currently unsafe system to a safe system on which no one can be severely or fatally injured on. And fortunately, there's been a lot of thinking about this. It started with the work they did in Sweden with Vision Zero, in Australia with Safe System, and in the Netherlands with Sustainable Safety, and in the US with Road to Zero and Towards Zero Deaths. And they all have a slightly different flavor to what they're doing, but they all have a common denominator that first they challenge our ability to reach zero without making a major change. And the second part is that they're all multi-layered systems approaches. They think about it from the perspective of the system. So what I'm going to highlight in the next few slides is how does this approach translate in terms of the safe system approach. And as I said before, Vision Zero, very similar, Sustainable Safety, very similar. And it all boils down again to human tolerance to physical force. And that's something that I keep on iterating in my talk, but it's also something that is consistent across these different approaches. So at the core, we have human tolerance to physical force. And as you can see around it, we have three components that I'm sure you all are aware of and have been thinking a lot about. The first one in the bottom right is safer roads. And that means that's the design of the road facilities. The second one is safer vehicles. And that's the design, crashworthiness, and other elements of the vehicle. And then the last one is safer speed. And we typically think about all of these. There's nothing new here. But what these approaches do, they remind us that it's not just about the individual capability of all of these. It's much more about alignment. So we want that the combination of the roads, the design of the roads, the design of the vehicles will be aligned with the speed that the vehicles are actually going. So it's not that we just want to reduce speed or we just want to increase speed. We actually want to manage a speed that would allow vehicles, pedestrians, bicyclists, would allow the mobility without compromising their inherent tolerance to physical force. This idea is, again, not new, and what I have here is two screenshots from a YouTube video about a very violent NASCAR Daytona crash. And in this crash, this specific driver crashed with another vehicle and then rolled over many times, including some of the roadside elements, probably 30, 40 times, a very, very violent crash. And at the end, the driver was actually able to take off the helmet, release or unbuckle his 5-point harness, and allow himself or pull himself out of the car and then walk to the emergency medical services. So even a crash of this magnitude, the outcome was that this person did not suffer a severe injury, maybe even no injury at all. So NASCAR and these type of races, they've already had that in mind, and they are going definitely at excessive speeds, but those are speeds that are aligned with what their system can accommodate as it relates to the roadside or the design of the roads and what the vehicle can do. So again, we need the combination of these three to protect human tolerance to physical force. I'll skip this a little bit because I want to be more mindful in time. How is that applied then to traffic safety, or how do countries such as Sweden use this information to set speeds? I'm sure you've all seen these slides before that allow us to calculate what is the probability of fatality for different type of users, unprotected, side collision with a vehicle, head-on or fixed object collision with a vehicle for different speeds. So then we're able to estimate that at 20 miles per hour, if the car hits a pedestrian, the probability of fatality is 10%. If we're going 30 miles per hour, it jumps to 80%. So that is what captures this human tolerance to physical force, and it's based either on crash reconstruction or simulation studies. So that's item one. Then what is done based on that, it helps identify what is an acceptable or a safe car can accomplish. So based on these curves, a safe car can protect occupants up to 45 miles per hour in a head-on collision. Similarly, it can protect occupants up to 30 miles per hour in a side collision, and what level of protection or at what velocity can it also provide protection to unprotected road users. And then what they do, they use that, or that's where the component of the safer vehicles comes in, because the vehicles have a lot of protective capability, much more to the occupants than to the unprotected road users. But again, it brings the idea that now we need to consider the cars. And then the last piece is, so what should be the speed limit given the human ability to sustain force, the vehicle design, then we set the speed limit based on that. So if we have roads like this, or rural roads, two-way, and we saw that at 45 miles per hour, the vehicle can provide protection to the users, then that's what we set the speed limit at. Similarly, if we have a much higher quality facility, such as the one here, they call it in Sweden 2+1 roads. So they have two roads in one direction, one in the other direction with a cable barrier in the middle, and then every few miles they alternate. And what that does, it almost eliminates head-on collisions, which we saw are the most fatal ones. So once that element is there, now they can increase the speed limit to 65 miles per hour because they're not going to be a lot, preferably no head-on collisions. So now we can afford to go at faster speed. So that's where the safer roads come in. So we're creating this triangle of roads, vehicles, and speed. Similar things are happening in urban environments, but over here they kind of just set the maximum, but they allow the agencies to reduce that even more based on some other guidelines that they need to consider. So we talked about what's at the core of this, and we didn't really talk about the users. And when we think about traffic safety, the users always come in. It's always about the users and a lot of blaming of the user's behavior. And the safe system approach actually recognizes that as humans, we're far from perfect. And the requirement is that the users are alert and compliant road users. What do we mean by alert and compliant? And I always like to use these minions to explain it. So here on the left, we have a goody two-shoes minion. And this minion is not me. And this minion has always had a full night of sleep, is always happy, is always on time, and he does things exactly as was expected. That's on one end. And on the other hand, we have a much more error-prone minion, which is a lot more like me. This minion's name is Carl, and Carl is always a little bit tired, sometimes gets emotional, a little bit late, and he's always kind of just not necessarily meeting all of the expectations for every single moment. There are times that Carl is doing it well, but every now and then he is going to mess up. And that is important because if we design our system for people like Phil, since we're not all like Phil, at some point we're going to mess up, and that will result in an unsafe system if we expect everyone to behave perfectly. But if on the other hand, we recognize that at some point we will make a mistake as a result of misjudgment, as a result of some instantaneous lapse of attention, we are much more likely to have a safe system because we've incorporated enough buffers to account for the offsetting behavior that some of these road users will do. So these are the guidelines, or these are the basic or the fundamentals of the safe system approach. And again, it's this triangle of safety combined with recognizing that the road users are going to mess up. So where do we go from here? And because even though this is clear, it's well articulated, whenever we come to talk about it with agencies, we can, okay, so what am I doing tomorrow? Or what does that mean for policy? And we haven't found a good way to answer that question, because the answer is, oh, we should aspire for 0 deaths, and we should just keep on doing what we're doing with more intention. But that doesn't necessarily give us the traction that we need. So what we're doing now in project that's funded by another national UTC, the Collaborative Sciences Center for Road Safety. We started a project that's attempting to develop a framework to combine these different protective elements or features of a safe system. And the way we're doing it, when we started, we tried, can we see if we can articulate what is the essence of the problem that we're trying to solve? And we took the case study of Cyclist, and we came up with this paragraph. What we want is alert and compliant riders to make trips using safe bicycles on safe street design with adequate separation from safe motorized traffic, driven by alert and compliant drivers, all of which are governed by safe speeds and supported by effective cyclist protection and the medical emergency system when needed. And we kind of went through several iterations until we landed on something that we think captures all of the elements that the safe system implies, but in a way that's much more conversational. And then based on that, we tried to refine and see, can we distill what that would mean in a way that we would want to quantify. And then what we came up with is these 6 safety considerations. Street design, and that's the actual design of the street, the lane width, shoulders, other aspects of the design of the street. Street operations, control, speed limits, and so on, all of the aspects that define turning movement, that's the operations. Then the street user behavior, that goes back to Carl and Phil, the fact that there's another layer of how we actually behave. Enforcement can help with some of that. And then number 4, street user warning. And that's something that in historical perspective is not thought about much, but with intelligent transportation system and technology, there are ways to incorporate more warning to the users when something goes wrong. And then the last 2 are street user protection. And it's anything from helmets, seat belts, and other protective components that are offered, airbags. And the last one is this last chance. When all of these fails, what we end up with is the EMS system, emergency medical services, and they can use their skill and capability to save a life or help someone not be a severe injury and a much lighter level of injury. So we were able to refine it to these 6 safety considerations, and they relate to different road users, going back to the beginning, how we're thinking about kinetic energy in the multimodal system. And then we started the effort of, and this is still ongoing research, and we started the effort of how can we combine these aspects together in a way that would be meaningful. And right here, I have it as protective capability of the system, but the factor research is aggregating much more the capability of the system in terms of kinetic energy units or units of kinetic energy. And the way we're doing it is that we're starting to provide some sort of estimate about the protective capability of these different considerations. So if we start with design, so providing shoulders allows someone to dissipate some of the energy if there's about to be a, let's say, back of queue crash. So there's more space to go to the side, dissipate that energy to slow down or even prevent a crash whatsoever. And it provides some level of protection. Street operations, again, traffic control, traffic signal, speed, all of these can provide another layer of more protective capability of the system. When we go to street user behavior, once we started doing this work, we saw that that actually has a negative effect. So the street user behavior actually reduces the protective opportunities of design and operations. If even if you just drank 1 or 2 glasses of wine, which is legal in all but 1 state, your performance is still diminished, and some of the safety buffers suddenly became smaller. Similarly, if you run a red light, again, you diminish these buffers. So the behavior is actually something that offsets the protective opportunity of these of the design and operations. Street user warning does the same thing, but in the opposite direction. So if there is an in-vehicle device that can warn you that you're about, that the crash might happen if you're not going to take any action, that is something that, again, can bring back the buffers to closer to where it should have been. If there are some warning systems within vehicles that a pedestrian is crossing and the driver did not see it, same thing. So it can apply for different modes. And in the future, some of these things can also maybe apply to on bicycles or on other modes, maybe even on pedestrians. So these are the first four, and we saw that they add and subtract in different ways. Then number 5 is the level of protection. I said that's helmets and seat belts and so on. And I've already incorporated the minus and the plus, because if you're not wearing the seat belt, you're offsetting some of that. But if you have something in the vehicle that warns you that you're not wearing your seat belt, you're kind of bringing some of that back. So again, protection is an inanimate feature that you can subtract from that or add from that. And then at the end, the emergency medical services, which I said is the last chance if all else fails. And the idea of what we're doing here is that we're combining all of these together to create some sort of level, some sort of, to quantify what is the capability of the system to provide protection. So what does this mean for policy? So before we can move that into the policy discussion, we need to better understand what we have, what is the empirical data that's out there. So to do that, we're actually looking at each of these combinations of different modes and looking at the crashes between them and are quantifying the level of kinetic energy that was carried as a pair. So if it's 2 cars, certain level. If it's cars and a pedestrian, certain level. Pedestrian with bike, a different level. So we're able to do that for each. This is just half because it does no longer matter if it's suffered or inflicted. But then we're able to quantify what is the level of kinetic energy that we're observing as it relates to these conflicts. And that tells us the levels of kinetic energy that the road users are exposed to across different parts of the network and across different mode pair combinations. So what are the policy implications? If we're able to quantify the level of kinetic energy carried by these different users and different conflicts that the empirical data tell us is being realized, then we're able to set the policy and say at these type of facilities where there's a lot of potential conflict between pedestrians and cars, we would want the system to have the ability to cover or protect us from this level of kinetic energy. Where on the highway, there should be a different threshold that is set. And then what we do, we add up, or we would be in a position, or this is more of an opportunity, to look at our roads, combine it with the vehicles and with the speed, and then see if we're able to add it up to a level, to a desirable level that's set by the policymakers and is stemmed from the observable or empirical data about the level of kinetic energy that's actually carried by the different road users. So to summarize, thought a little bit about what are the takeaways from this talk, or as Track described it, the learning objectives. And the 3 things that I thought are most important to take, or the goals, were to understand what is a safe system approach to road safety, and how is this triangle of safety of road design, vehicle design, and speed is at the core of providing the level of protection to humans, and then how on top of that the layer of behavior comes along. Then the second part is to recognize the different roles of the core protective opportunities provided by the system and the challenges that we're actively dealing with to aggregate it and to quantify it. And then the last part is to appreciate the policy opportunity created by adding non-crash safety considerations. Today, what we do, we just quantify the outcome. We want to get to 0 deaths, but that's what we count. We just count the number of deaths, and when it goes down, we know we're moving in the right direction. What we're claiming here is that it would make more sense for us to set the threshold. This is the level service, if it's appropriate to use that term, but this is the level of safety that we aspire to. We want the system to be able to provide this level of protection. And then that's something, if that's something that you can actually measure, then each of the parties, each of the agencies that are involved in this process can have a more defined role and don't necessarily roll over the responsibility. Oh, it's a driver, so it's a more behavioral thing. Or, oh, that's the transportation agency, their roads are not designed well. Oh, or that's the regulator, the vehicles need to be safer and so on. This way we can kind of demonstrate that this is a system perspective and all of these different partners need to work together so that their aggregate impact meets a certain threshold. Thank you.
So we do have time for questions.
We do have time for a few questions.
My guess about background here is that the research you're doing about motor vehicle users and controlling them would be requiring smart systems in vehicles. So GPS locators, cell phone, car-to-car, or peer-to-peer communication, etc. Now, the biggest pushback that people have is they don't want for-profit companies knowing what they're doing with their motor vehicle. They don't want it like Chevrolet or Ford or Tesla know where they are and where they're going, why they're doing, etc. So putting peer-to-peer communication in cars has a big pushback, and people don't want necessarily the traffic system to know that they passed this mile marker. And the same thing with the electronic tolling. People don't like it because they don't want to be under the control, perceived control of somebody else. So how do these types of technologies going to come out? If you're trying to develop a system, how do you get around the user resistance to those technologies?
So over here, we haven't offered anything that would require GPS or peer-to-peer communication. So when I'm talking about the intelligent transportation system component here, that would have some sensors in a vehicle or another mode that are able to realize that there is an undesirable proximity to another entity, can be a pedestrian or a car, and would provide a warning. We're not even advocating for action, even though that is something that can be and has a lot of value to incorporate. But what we are advocating for here is to provide warning when it can be provided by technology to compensate for the lack of attention that field can occasionally have. Now, a peer-to-peer communication, the impact that can have on safety is huge. But of course, there are many other things that need to be discussed. But it's not part of this framework currently at all. Thank you. Yeah.
I'm curious whether or if mode split factors into this analysis, because we know that many cities are trying to dramatically reduce motor vehicle use, mode share. So if the level of cycling and walking and transit dramatically increases, and the number of cars on city streets decreases, does that change any part of this analysis?
Absolutely. So as you may have noticed, we haven't fully figured out how to add it all up. But when the mode mix or even the built environment changes, when these things change, it is something that can develop with that. Because if you remember, we are looking at what the empirical data tells us about mode pair conflicts. And if we combine that with information about mode share, then an agency can say, or a state can say, in our state, the mode share is now larger. So now it's met a certain threshold that for these type of facilities, we now want an even higher threshold to be able to contain, because we have a lot more of unprotected users. So if this is an area that is very rare to see a pedestrian at, then we can just, with the vehicles, we're able to account, vehicle to vehicle, we're able to account for a much higher level of kinetic energy. If one of these users becomes a pedestrian, we suddenly, that person is no longer protected, so we need to change the threshold of protection that we want. So it can respond to that. Not sure how to do it quite yet with the in theory. Yeah.
I was hoping you could go back to a slide on protective capability of the system and other safety considerations. Yeah, I guess I was wondering about the degree to which you've researched the relative size of those bars.
This is almost intentionally arbitrary.
Okay.
So the parts that we know the most about are these. We know some about the operation and the design. That's the part that's hardest to quantify. And the sizes here are intentionally arbitrary. That's the challenge that we're working on now. So for the protection, there are lots of studies and lots of simulation models that tell us what amount of kinetic energy is absorbed. When it comes to things that are more in the pre-crash term, that's where the research challenges comes in. And these values, I'm glad you asked, I should have mentioned that these values are completely arbitrary.
I do have a question. Do you have a theory why the fatality rate has been dropping with PDT, the statewide data? You see 2 trend lines. The PDT has been climbing. So the fatality rate, do you have a theory why that's happening?
Maybe, I'm not quite sure, but maybe the level of, so it's dropping for vehicle occupants, and it's not necessarily dropping for unprotected. So what might be happening is that the level of protection that's provided by the vehicle actually surpasses what many of the regulators are asking for. And it has come to provide a much better level of protection. And the fact that for pedestrians and bicyclists it's not quite the case is potentially some combination of motion. There are more out there, but also the level of protection hasn't quite caught up. But I don't really know. Yeah.
I'm thinking about traffic calming and how effective that can be after the fact, applying findings to an environment afterwards versus building it from scratch.
So as it is captured in this framework, wouldn't make a difference. We won't be able to, if you apply traffic calming, the speeds will go down, and then the amount of empirical kinetic energy that are carried will be decreased, and that will affect that. But what I think you're asking about is more if you do it ahead of time, the behavioral response is one way. If you do it later on, the behavioral response will be in another way. And kind of this is absolutely not able to capture that. But I'm not sure. I'm not sure what would be the difference. But this cannot help solve the question. Yes.
I was wondering, I was just thinking of different safety provisions in the safety center, and does, I almost want to wonder if like a seventh, like the transportation environment, like I'm hoping to see that alcohol-related crashes could decline as like Lyft and Uber and more young people taking taxis, or even better transit options for aging populations who should commit to driving cessation. Is that in this framework, or is that more like outside of it?
No, so it fits in through the subtraction of the behavior component.
Okay.
So if people are no longer, if there's zero tolerance for drinking, then the offsetting of the behavior, the offsetting of the protective capability of the behavior is going to be much lower.
Okay.
And yeah.
Thank you. Thank you.
Okay, let's give Dr. Grembek another round of